Hello and welcome. In this video, we're going to take a look at the graphs of common trigonometric functions. Based on what we've already found out about the values of trigonometric functions going around the unit circle, it's time to take a look at what the graph would look like. Seeing as how we can choose any real number for t and evaluate sine t, cosine t, tangent of t, and all the other ones, why don't we take a look and see kind of what the behavior of these functions would look like. And the major ones to focus on would probably be sine, cosine, and tangent. So let's take a look here. Sine and cosine, we know, repeat once every time around a circle. So we say that they are periodic functions. They have a period of 2 pi. Every time that we get to some new value of t, then the function has exactly the same value as it did 2 pi before that along the t-axis. So we could say that sine of t plus 2 pi is just the same as sine of t, and cosine of t plus 2 pi is just the same as cosine of t. And in fact, that can be even expanded. Sine of 2 pi n, where n is any integer, is also just sine of t. Okay, well, let's take a look at some of the common sort of terminal points as we go around the unit circle. And if we can remember those numbers for the y-coordinates, then we can plot the graph of sine t. Now, remembering that sine of 0, since it's the y-coordinate of our initial point, just starts at 0, we can then see that through quadrant 1, the y-coordinates are increasing. Sine of pi over 6 is 1/2, sine of pi over 2 is root 2 over 2, sine of pi over 3 is root 3 over 2, and finally sine of pi over 2 is 1. And that's just what I've got here as the first quadrant in red. And we could plot those points with values of t and our y-coordinates, and they are gradually approaching 1. Now when we get into quadrant 2, the y-coordinates start at 1 and reduce themselves as we go around counterclockwise to 0. So you can see we end up going through the exact same y values, but we get closer to 0. And then along the bottom half of the circle, through quadrant 3 and quadrant 4, we, of course, just repeat the same values, but this time they're going to be negative. So you can see that we have a half of a wave above the x-axis and then another half wave that is sort of symmetrical. It's got the exact same shape just below the t-axis because we have negative values of sine in quadrants 3 and 4. And then using the general shape, we can get to quadrant 1, 2, 3, and 4 once more after we've gone past 2 pi. We just go and repeat ourselves. Now, if we want to, we can do a very similar process to come up with the graph of cosine of t. Now, with cosine of t, we're looking at the x-coordinates as we go around the unit circle. And so our x-coordinate at our initial point when t is equal to 0 is going to be 1. So this graph would start at the point 0, 1. And here I'm labeling the vertical axis as x as a reminder that we're thinking really about the x-coordinates on the circle x squared plus y squared equals 1. Now, going a little bit further into quadrant 1, when t equals pi over 6, cosine of pi over 6 is root 3 over 2. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 3 is 1/2. And finally, when we get to cosine of pi over 2, we get an x-coordinate of 0. So in quadrant 1 here in red, you can see that our values are slowly decreasing until we get to 0. In quadrant number 2, though, we have to remember that cosine is negative. It's going to repeat the same values, but of course, we're having all negatives, and we're going to have negative 1/2, negative root 2 over 2, negative root 3 over 2, and finally negative 1 when we look at cosine of pi. And quadrant 3, we're still negative, but we're getting closer to 0 as we go counterclockwise around the circle towards 3 pi over 2. And at 3 pi over 2, we have an x-coordinate of 0 on our terminal point. And then we quickly get back to where we started when we reach t equals 2 pi. And then we'll repeat the same shape again. Now, both sine t and cosine t are defined for any real number. We've already taken a look at what happens if we find cosine of some number that's not within 0 to 2 pi. Well, we can always find a coterminal angle. So the domain of these two functions would be all real numbers. But looking at points on a unit circle, especially since we're talking about a unit circle, we know the radius is 1. The x and y coordinates can never be larger than 1. So the range of sine t and cosine t are both -1 to 1, including those values. So in the following chart here, we can say the domain is all real numbers, but the range is only between -1 and 1 inclusive. And both of these functions repeat themselves once around the unit circle with a period of 2 pi. Or in other words, we could say that they are 2 pi periodic. Now, because of this nice wave form here, we have a half wave going up as far as +1 and a half wave going down as far as -1. If we measure from a central axis here, which we have as the t-axis, we would say that the amplitude is equal to 1. So for both of these functions, you can see an amplitude of 1 above and below our t-axis. Now, in general, anytime that we have some sort of waveform like this, and we can have a sinusoidal waveform or a cosinal waveform, we could even talk about other types of waveform, but really anytime that we have a half wave up and a half wave down, then we say that the amplitude is equal to the height of the wave. Or in other words, it would be the maximum value, 1, minus the negative value, -1, and then divide the value by 2. So amplitude, we can think of as the height of one of these half waves, or a value halfway between the maximum and minimum values of the waveform. Now, with sine and cosine, the amplitude is 1. But of course, what we can do is then we can take a look at transformations of graphs. And we're going to look at a few transformations really in particular here. We'll look at stretching or shrinking the functions vertically, and that's going to affect the amplitude. And we're going to take a look at stretching or shrinking the function horizontally, and that's going to affect the period, or how often the function repeats itself. And then we'll take a look at shifting this function left or right. And that's a horizontal shift, but when we are referring to sine and cosine, we tend to call that the phase shift. Suppose we start off with our function either as sine or cosine. If that is our function f of t, then remember our transformations of graphs. If we take f and we multiply the whole function by a, then that is going to be a vertical stretch by a. If a is larger than 1, then the graph gets stretched vertically. But if a is between 0 and 1, then this is going to end up being shrunk and getting closer to the horizontal axis. So this is going to affect our amplitude. Our original functions have an amplitude of 1, and our new functions will have an amplitude of a. Now here I'm writing the absolute value of a because let's suppose a is a negative value. Well, that's simply going to flip the graph over the t-axis, and it will have the same half-wave height above and below. So we'll just treat amplitude always as a positive number. And again, remember what happens if we take t and we multiply that by a constant. Well, that is going to stretch or shrink, but it's a little bit backwards. When k is greater than 1, this is going to take our graph and shrink it horizontally closer to the vertical axis. And if k is between 0 and 1, that's going to stretch our graph away from the vertical axis. If k is negative, that is going to flip the graph. But flipping the graph over the vertical axis doesn't change the period. Only the action of stretching or shrinking the graph is going to affect the period. So we know the old period is 2 pi. That means that for our transformed graph, if k is larger than 1, the period is shrunk. If k is smaller than 1, the period is stretched. And the new period is 2 pi over k. And last but not least, whenever we have t minus some constant, well, here we have a minus sign, and that is really just so that it hopefully clears up a little bit of confusion. Whenever we take a function of t and we do a transformation of the form f of t minus b, assuming that b is a positive number, t minus 2, for instance, that's actually a shift to the right. It's going to shift right by b. If b is a negative number and we have t minus a negative value b, well, then that's going to look a lot like just t plus b, obviously. But that is going to be a shift to the left. So having this minus sign there can be a little bit helpful. Our original graph isn't shifted at all. So our original functions sine t and cosine t, we say have a phase shift of 0, or no phase shift. But in the case where we do have t minus a constant, our phase shift is b. So b could be positive or negative. If we have t plus 2, that's going to be a phase shift of negative 2. And if we have t minus 4, then that's going to be a phase shift of positive 4. It's really important to remember that whenever we are having a combination of horizontal shifts and horizontal stretches or shrinks, we should really be factoring out that horizontal factor first. Then it's easy to see that we just have t minus b, and it's the b after we factored out that stretch that gives us our phase shift. Now to demonstrate this, I'm going to go ahead and try out a few little manipulations of sine t with you on Desmos. And you can try this out for yourself. You can just go onto a browser and open up Desmos and try it out by putting in a few transformations. So here I've got Desmos in a browser, and I've put several different plots on here for us. So f of t, that's our function, and I have a times sine of k times t minus b. So you can see that we've got a combination of a vertical stretch, a horizontal stretch, and we've got a horizontal shift. But currently, based on the slider values down here, I have a equals 1, I have k equals 1, b equals 0. Plugging those numbers in, currently I just have sine of t. And along the horizontal axis here on my graph, you can see I'm going up by pi over 6. Sine of pi over 6, perfectly 1/2. Sine of pi over 3 isn't a nice number, root 3 over 3. Sine of pi over 2 is 1. And that's the first quadrant. It's the first little bit of the hill. Coming down from the top of the hill back to the t-axis. Well, that's quadrant 2. And then going down to the bottom of the valley, that's going to be quadrant 3. Going from the bottom up to 2 pi. That is going to end up being our fourth quadrant. And so I've included these little dotted lines, blue dotted lines and green dotted lines, so you can see exactly that one period of sine t goes from 0 to 2 pi and has a range of -1 to 1. Now, let's start adjusting these little sliders and see what happens to amplitude, to period, and to phase shift. So the first thing I'm going to do is I'm going to mess around with the slider bar here for A. Watch what happens as I increase A. And I think I'm going up here by, 0.1 at a time. When A is equal to 2, you see the amplitude has changed to 2 now. If A is going to equal 3, my amplitude is 3. And going to smaller numbers, 0.4, 0.5, you can see that my amplitude now is exactly 0.5. And if I go to 0, then I don't really have a sine graph anymore. I've just got a horizontal line. But if I go into negative values, I have flipped my sine function upside down. Letting a equal -1, I end up with the sine graph upside down. And notice that by odd symmetry, the graph of sine t flipped over the t-axis is exactly the same as the graph of sine t flipped over the y-axis. Okay, that's exactly what odd symmetry is. Flip vertical is equal to a flip horizontal. All right, now I'm going to put that back for a moment and watch what happens as I drag the slider for k. As k increases, our period is 2 pi over k, so the period is going to decrease. If I increase k as far as 2, you can see that now I complete an entire period of sine from just 0 to pi. And this is the graph of sine 2t. If I go as far as sine 3t, then my graph repeats itself in exactly 2 pi over 3. So there's your calculation, 2 pi over k. And another thing you can think of, if k is equal to 3, I get 1, 2, 3 periods in the time that I would normally get a single period. All right, now if k gets smaller, and I maybe reduce it back to 1 first so we can see the original graph. If I now bring this down to 0.5, watch how quickly the graph stretches out. Now I only create a half wave from 0 to 2 pi, and my other half wave starts to get off the screen here and isn't going to complete until I get to 4 pi. There we go. Now I'll put that back again. Put that back to 1. There's my standard graph. Now I'm going to start adjusting the phase shift. Now the phase shift, I've got this set up as t minus b. If I start increasing b, I'm going up right now by increments of pi over 6. Pi over 6 is not a nice number, 0.523. You can see my graph has moved to the right pi over 6. That's a phase shift. But my function right now is actually sine of t minus pi over 6. So that's a little bit peculiar. You have to remember that that is shifting it to the right, t minus pi over 6. T minus pi over 3, t minus pi over 2. Eventually I can go to t minus pi. T minus pi has now shifted the graph all the way for graph from pi to 3 pi. Okay. What if I shifted the other way? Now this is t plus pi over 6, and b right now is negative pi over 6. My phase shift is negative pi over 6, and the graph moves that direction. Negative pi over 3, negative pi over 2. And so you see my b is negative 1.57, which is pi over 2, and my graph right now is sine of t plus pi over 2. Now this should look familiar because this is actually the graph of cosine. And so that gives us a nice little identity. Sine of t plus pi over 2 is equal to cosine t. Now we can put all of these transformations together. And when you're plotting something, if you have a function with changes of amplitude, period, and phase shift, it's always best to do them in this order. Amplitude first, because you'll have to make sure that you're stretching away from the horizontal axis. So worry about your amplitude first. Let's say the amplitude is 3. Then make sure you factored out whatever scale you have for the horizontal axis. If you are scaling the period, you need to figure that part out first. So let's shrink this graph in so that we actually have a period of pi now. And then we can go ahead and start shifting the graph to the right. Look at all the transformations we've got together here. The original graph is really now from pi over 2 to 3 pi over 2, which is a period of 1 pi. You subtract 3 pi over 2 minus pi over 2, you'd get 2 pi over 2, and that is exactly 1 period. That period has been shifted to the right, though, so it's not starting from 0, 0, it's starting from pi over 2, 0. That's our initial point now. We've sort of shifted the whole graph. And last but not least, of course, we've got the amplitude, which is really the only thing we're doing to this vertically. And there we go. Now it's really the same thing. If I wanted to maybe zero these back out again, return the amplitude to 1, and return our period to pi, and change our phase shift back to 0. If I were to do the same thing with cosine here, nothing is really any different except for the fact that we have to start at the point 0, 1, amplitude, period, and phase shift. They work exactly the same way for cosine and sine. But now let's take a look at tangent. And so let's go back to the notes here and see if we can figure out what the graph of tangent looks like, and then maybe we can come back and play around with some transformations. Now thinking about the graph of tangent of t, we have a few points that we can refer to around the unit circle. When t equals 0, tangent of 0 is 0 because we have tangent t as being y over x, which is 0 over 1 at the initial point. At pi over 6, using y over x, or sine over cosine of t, then we end up with root 3 over 3. And tangent of pi over 4 is 1, since the x and y coordinates are the same. Tangent of pi over 3 is root 3. Now it gets a little bit tough, because when we try to plug in t equals pi over 2, tangent is undefined. But watch what happens as we get closer and closer to pi over 2. So why don't we start off by at least plugging in something fairly close to 1.57. We could start by plugging in 1.5 and evaluating tangent of 1.5 in radians. We can see on a calculator we get 14, which is crazy because sine and cosine never have values in their range larger than 1. So tangent is already pretty unique. when we go to 1.57, we're still a little bit shy of the actual value of pi over 2, but we're getting really close to it now. And you notice that when you plug this into your calculator in radians, 1,255.77. And this is because our y-coordinate on the unit circle is getting closer to 1, but the x-coordinate is getting closer to 0. Now, 1 divided by a very tiny number, but not quite 0, would still be defined, and it would just be a really big number. So as we get closer to pi over 2, we're going to see this number get infinitely large without bound. Now, this isn't an actual point on the graph. We can't say we have the point pi over 2 and infinity, but we can say that the value of tangent of t is getting infinitely large. Now, combine that with a few other facts that we know about tangent. We now know that tangent of t has a vertical asymptote at pi over 2. Closer we get to it, the larger we end up with, so we have a vertical asymptote. We say as t approaches pi over 2, tangent of t gets infinitely large. We also know that we only need to go around the circle halfway through quadrant 1, quadrant 2, before we end up with a repetition. The tangent of t is y over x, and we start off with y being 0 and x equaling 1, and we end up at the end of quadrant 2 with, again, y equaling 0, but this time we have x equal -1. But as soon as we drop into quadrant 3, we're going to be starting with small y values and values of x close to -1, and they're both going to be negative. That makes tangent positive in quadrant 3. We end up with exactly the same ratios as we did in quadrant 1. So it has a period of 1 pi instead of 2 pi. Every time we go around the unit circle halfway, then tangent of t will start to repeat itself again. In other words, tangent of t plus pi is equal to tangent t. And we could generalize that. Tangent of t plus any multiple of pi is also equal to tangent of t. And one other fact about tangent of t is that it has odd symmetry. Tangent of a negative t, that's maybe going around in the opposite direction, is equal to a negation of the value of tangent of t in the other direction. So in quadrant 1 and 4, tangent has opposite sides, and in quadrants 2 and 3, tangent has opposite sides. So if we go around in the unit circle in a different direction, all we have to do is negate the signs of tangent of t in the proper direction. All right, with all of this in mind, we could just plot a very small portion of the graph of tangent t just for the values of t in quadrant 1, and then use symmetry and repetition to get the rest of the graph. Plotting the values in quadrant 1 here, we see tangent of 0 is 0, tangent of pi over 6 is root 3 over 3, tangent of pi over 4 is 1, tangent of pi over 3 is root 3, and tangent of pi over 2 is undefined, but we do know it's got a vertical asymptote, and t approaches infinity as t gets closer to 1/2 of pi from the left-hand side. All right, well, using some symmetry here, if we have odd symmetry, then that means that if we reflect our graph over the vertical axis, it's equivalent to flipping over the horizontal axis. And we would have to have symmetry through the origin then. So that means you can see that we have a graph that continues straight through the origin and actually tends in the opposite direction on the negative side of the t-axis. Now the good news is here that this will actually give us a full period of pi to work with. From negative pi over 2 to positive pi over 2, that is a total distance of 1 period of tangent. And because it has a repetition, we already know what that repetition looks like. We can then plot one more period. And that's going to get us from pi over 2 to 3 pi over 2. Now we'll have exactly the same shape. And if we want to continue to graph this all the way up to 2 pi, then of course we can just continue to have repetition. We only need half of one more period to get as far as 2 pi, but it would continue to repeat with the same sort of overall shape over and over again. There are some noticeable differences with the graph of tangent compared to the graphs of sine and cosine. First of all, thinking about the domain, there are many vertical asymptotes. There's infinitely many vertical asymptotes on the graph of tangent of t. The vertical asymptotes occur at pi over 2 plus any multiple of pi. So unlike sine and cosine, the domain is not all real numbers. However, taking a look at the range, since we have these vertical asymptotes, we can see that this graph has a range of negative infinity to positive infinity. So it actually has a range of all real numbers instead of just being limited to -1 to +1. We can also not really talk about amplitude because this isn't exactly the nicest looking wave like sine and cosine are. So we don't have a maximum and minimum value. We can't compute amplitude. But if we want to take a look at transformations of graphs, we could still be talking about period and phase shift as kind of the two big things that we can change through transformations. So I'll turn the video back to Desmos here. We'll take a look at tangent and see what happens if we were to adjust the horizontal shift or phase shift, as well as the horizontal stretch or shrink, which would affect the period. Okay, so in Desmos now, I've just changed the function so we have the graph of tangent of k times t minus b. I'm not using a in the front because that is changing the amplitude of sine and cosine, but for the graph of tangent, it's merely just a vertical stretch. It doesn't really have any meaning about amplitude. You can see I've included two vertical dashed lines here to indicate those asymptotes at -π/2 and +π/2. The graph, our red function here, doesn't actually include those lines, but I'm just putting them on there for convenience. Now I've got a slider here for k, and notice we have currently a period from π/2 to π/2, which is the length of 1 pi. But if I make k larger, then we start to shrink that period. So if I let k equal 2, this is actually now changing the asymptotes at -π/4 and +π/4, which is now only a period of π/2. Let's go and put this back to a normal period of pi. There's my normal graph. What if I shift this forward by π/2? Well, this is now a graph that has a vertical asymptote at t equals 0 and t equals pi. So by shifting, I've moved these asymptotes forward, and by stretching, I move the asymptotes closer or farther apart. Now, as an added bonus, we remember how sine and cosine are merely a small shift away from each other by π/2? Well, if I take the graph of tangent of t and I shift it to the right by π/2, now this is the graph of tangent of t minus π/2. This is actually the graph of cotangent. So there's an added bonus. I didn't necessarily want to throw that in the video here, but you might as well see what the graph of cotangent looks like, because it's pretty much the same as the graph of tangent, just with a tiny little shift. Now the graph of secant and cosecant aren't the nicest. You can go ahead and try those here in Desmos if you like. It's pretty easy to open it up and type in a function and it will plot it for you. And those are also graphs that have asymptotes as well. I personally find that we don't often need the graph of secant and cosecant. We tend to just think about secant and cosecant as being reciprocal functions of cosine and sine. So whatever the values were on those waves, by taking the reciprocal of them, we'll get the graph of secant and cosecant. And that's also going to tell us where we're going to end up with vertical asymptotes. Now, I will say the graphs of sine, cosine, and tangent are pretty essential to just know off the top of your head. You should at least be able to reproduce a relatively decent sketch of those three functions. And that's not just because, well, you're asked to sketch them, but it's also really useful just for remembering the values of sine of 0, π/2, pi, 3π/2, and 2 pi. Because if you just remember it goes up, down, and up, it's 0, 1, 0, -1, 0. So then you can just remember sort of the major four quadrants as we go around every quarter of the circle. Same thing with cosine, 1, 0, -1, 0. So it's really helpful if you can just draw a quick little sketch of those things so you remember some of the major important values of cosine and sine. Well, we'll play around with some of the inverse functions in another video. It may have some interesting graphs as well, but we'll take a look at that in the future. So thanks for watching, and I'll see you in the next video.